Hello everyone, I'm Yiyu. I'm a PhD student at the University of Washington. I'm going to discuss some of our results on depth Wavefield reconstruction using machine learning methods. In this presentation, I will discuss how machine learning methods can be used for lossy data compression and Wavefield separation. So we know depth is a technology that turns an optic fiber into string-sensor arrays. It has improved our understanding of ocean and earthquake wave phenomena by providing a dense observation, especially in the offshore area. However, due to its high spatial and temporal sampling rate, the data volume of a typical depth experiment is big, usually at terabyte scale. This clearly causes issues for data streaming and limits time-sensitive applications. This also applies to our ongoing depth experiment in Alaska's Cold Inlet. Beginning June 2023, the UW Fiber Lab team said use a seafloor telecommunication cable owned by GCI Corporation for continuous data acquisition. We used 10 meters channel spacing and 24 meters gauge length setting. Figures here shows a map of the cable surrounding earthquakes in the USGS catalog. On the right is a 10 meters recording and water depth profile from one cable called KKFLS. We have another cable, Terra, for acquisition at the same time. We can see that the cable features shallower water depth profile, higher noise, and clear bidirectional ocean wave pattern. On a daily basis, we stream back window data of new events in the USGS catalog. Until the end of 2023, 6 months of data recording, we sent back more than 2,600 events. The raw 25 Hz continuous data stay in the storage server co-located with the interrogator. Every day, there are about 73 gigabytes of data generated for each cable. This forms the original motivation of the study to explore if we can compress such a huge amount of data for streaming using machine learning methods. Here, we use a machine learning model called shallow recurrent decoder, or SHRED. The input of the model is a time series or trajectories from several sparse sensors. The LSTM takes the time series into the latent space, which is equivalent to a data dimensionality reduction step. The shallow decoder will map the latent space back to the full wave field. The SHRED model has shown promising results in reconstructing turbulent flow, global sea surface temperature, and atmospheric ozone concentration. So our idea is that we can decimate the raw depth data as a form of compression. Later, we can use the model to reconstruct the original data as a form of decompression. This is how we design the SHRED model for DAS. On the left-hand side, we have 200 sparse channels decimated from the raw data with 1,000 channels. The SHRED model takes a time series from these sparse channels as input and reconstructs the wavefield snapshot at these 1,000 channels. So our model is self-supervised, so no human labeling is needed for training. We use mean square error to measure the difference between reconstruction and raw data during the training process. We use the 6 months of window data for model training, validating, and testing. This is equivalent to 88 hours of continuous data. Demeaning and normalization are performed on each channel as a pre-processing step. We further perform data augmentation by random sampling the recording, shown as this is red patches. Each patch contains 8 seconds time series from 1,000 channels. Inputs are evenly decimated from these 1,000 channels. After all this step, we have a diverse dataset, making the model generalizable across spatial and temporal dimension. After training the model with using the data from KKFS cable, we are showing the reconstruction using a 10 minutes continuous recording. We can see that the overall temporal wave field pattern shows a good match. Moving towards the channel spectra, the low frequency content contributed by the ocean surface wave is well reconstructed. There is a cutoff frequency about 0.15 to 0.2 Hertz, and our model is having difficulty for the content above the cutoff frequency, especially above 1 1 Hz. We also performed the test using data from another cable, Terra. The model shows similar performance at handling complex ocean wave and instrument noise. Similarly, the model is having difficulty at higher frequency. We further analyzed the frequency spatial content of the wavefield. We selected 2,000 channel segments, decimate, and reconstruct the data. Then we transformed data into frequency wave number or FK domain. We can see that the theoretical ocean wave dispersion matches well on both raw and reconstructed data. The seaward wave is weaker than the landward wave. Its energy on the FK plot is still reconstructed in good quality. The reconstruction of the ocean wave also enables us to explore the limits of data decimation. Previously, we were using 20% channels for reconstruction. In this test, we reduced this number to 10% and retrained the model. We can see that in the reconstruction FK, there are artifacts shown as overtones of the dispersion curves. This model also fails at identifying the ocean wave propagation direction. This effect can be explained by the over-decimation, which limits the minimum wavelength we can resolve. Using 10% channels for reconstruction, the effective channel spacing increases to 95 meters, which corresponds to a wave number of 0.066. This is exactly where the first overtone artifacts start to show. Therefore, the FK content of the ocean wave effectively sets the reconstruction limit of our model. Okay, so after the effective reconstruction of the ocean wave, now we are curious about the residual. When training the model, we use the mean square error as a loss function, and the optimizer will update the model so that the residual should be as small as possible. However, there are sometimes spikes in the loss function, for example, the jumps around 10 seconds here. The channel spectra also confirms that 1 Hz spectra is not reconstructed well. So we are curious if there are earthquakes arrivals or coherent ambient noise in the residual. Here, we enhance the color scale to amplify the higher frequency content. We can clearly see a transient earthquake arrival, later confirmed to be the S-wave arrival from a magnitude 1.9 earthquake 60 kilometers beneath the Cook Inlet. At this point, we say that shred is separating low-frequency ocean wave and high-frequency seismic wave field. We examine if we can detect events on the residual. We use the kurtosis, which is a measurement of the data distribution. So if there's no transient signal, kurtoses tend to be small and not changing dramatically. This is the case on the raw data and the reconstruction data, where there's no clear change in the theoretical arrival window. However, on the residual data, even there's no filtering performed, we can still see dramatic change of the kurtoses in both P and S wave arrival window. We further calculated how much kurtosis has been improved in the residual on 400 catalog events. We calculate the kurtosis contrast between the arrival window and the noise window for both the raw data and the residual data. Each of the circles here shows an earthquake event. Those events above the red dashed line indicates an enhanced onset. About half of the events show improved kurtosis in the P arrival window. The improvement on the S-wave window is more significant, especially for those events larger than magnitude. About 75% of all events shows an improved kurtosis from the noise window due to the higher sensitivity of the optic fiber to shear wave motion. At last, we employ the ensemble learning earthquake phase picking algorithm to pick the arrival time on the depth data. The phase pickers are fully trained on high-pass broadband dataset and is not transfer learned on any depth data. We test on the raw data, and very few arrivals are picked due to the dominating strong ocean wave. Then we test on the residual data after removing the shred reconstruction. It turns out that we can correctly pick the arrival for both P and S wave. Further analysis of the difference between the theoretical arrival time and our machine learning picking shows a half-second travel time delay. In summary, the test showed that shred model together with the machine learning phase picker can be used for on-site event detection, especially in a real-time setting. Okay, to conclude our study, we use shred model to reconstruct low-frequency ocean wave signal. This is equivalent to a lossy data compression method with only 20% data needed. Second, the shred model enhanced the high-frequency transient earthquake arrivals in the residual that the model cannot reconstruct. This is effectively separating the seismic wave field from the strong ocean wave. Finally, the shred model is a large-scale machine learning model and may show great potential in time-sensitive applications like earthquake monitoring. Thank you for your time.